Welcome to video number 3 in the Microfluidics course. So here's a breakdown of what we're going to be covering in this video, and we're going to be looking at dimensional analysis. And we're going to really see the power here of non-dimensionalizing things and scaling arguments. So we've read through a few important papers in this course so far, and one thing we can notice is just how much scaling analysis is mentioned. And this comes up all the time in our engineering problems where we see dimensionless parameters or discussion of scaling. And what we're going to do with this dimensional analysis is we're going to develop a way of thinking where we can take the dimensions of a problem, and just from the dimensions alone, we can figure out a huge amount of information about what the solution is going to look like. So actually in 1915, Lord Rayleigh wrote this article in Nature called The Principle of Similitude, and he talks about how dimensional analysis is really powerful, especially for engineers, because just by looking at any problem, understanding the dimensions, we already know a lot about the form the solution is going to take. And he gives a number of great examples in that article as well. So I'm going to start with a look at non-dimensionalizing the basic differential equations we have for fluid mechanics. So remember, again, we're talking about microfluidics, but you're going to see from a number of these examples, and from the fact that we use these differential equations in a number of different fields, dimensional analysis is hugely broadly applicable. Okay, so I've written out the governing equations here for steady incompressible 2D flows. So that's our mass balance, and that's been simplified, of course, with those assumptions. U and V here, that just denotes the x and y components of the velocity vector. And in the momentum balance, I've written out, so we're 2D here, so I've written out the equation for the x direction and the y direction. Those are also called Navier-Stokes with those assumptions in place. Okay, and now we can go ahead and non-dimensionalize this, and we're going to see where that takes us. Okay, now we start by non-dimensionalizing each variable, and we do that with reference values. Now, the basic idea here, so ideally each variable goes roughly from 0 to 1. We definitely want to try to keep all of these to order 1. So I'll write these out, and as I write like x prime and y prime, so the prime one, that's the dimensionless one. So we're writing L here, where capital L, that's what I mentioned, that's our reference value. And so basically any problem you're dealing with, L is going to be the dominant length scale. And what I mean when I say that, so if we have an example, like say something's flowing through like a square tube, for example, then we'll scale our dimensions relative to the size of the tube. So L, for example, might be the height and the width of this square tube. V infinity, so in fluid mechanics problems, we call that our free stream velocity, and that's just the natural velocity of our problem, again, sort of far away from any structures or any interference. And then we have our rho V infinity squared term, that's what we're scaling the pressure to, so that's a free stream dynamic pressure that we're scaling against. So I'm going to do 2 examples of how we would substitute these in to the differential equation. I'm not going to do every single term because they follow the same basic format. So I'm going to write this out here. I'll pick u die x, and I'll go ahead and sub all these in, and we'll see what we end up with. I'll do another one. I'll do one of these second order differentials so we can see how that works as well. So the die squared u over die x squared. Okay, now once we do all those substitutions, we've maintained the dimensions of the problem, but now we have all the variables in their non-dimensional format. And we'll see why this is powerful in a second. So let's rewrite the mass balance here, subbing in, right, all of the dimensionless versions of our variables. Okay, now we can group this and cancel off the common terms. So everything is multiplied by V infinity over L, but the right-hand side is 0. So we know to have a meaningful solution that we can't have the V infinity over L being 0. So we can cancel those off. And there's our final mass balance there. So we'll do the same thing for momentum. I'll go ahead and substitute in with, the same basic format that I use to sub into the differentials that I just showed you. I'm going to go ahead and sub all these in. That's an exercise you can do yourself too if you want to try a few of these terms and see if you can get it. Okay, now we regroup and cancel these. And so this is where it's really interesting to take a look at this. So I'm going to rewrite the momentum balance where we've regrouped this. And let's take a look specifically at the y equation. So what has happened with this grouping here is each of these terms is dimensionless. And so we have these dimensionless groups. And I'll circle this one here. So this one, we can probably tell from the terms in it. So what this represents is the gravity forces. Okay, and I'll circle this one here. You probably recognize this already. So this is the inverse of the Reynolds number, right? So the way it's written here is actually viscous forces. We know that because the viscosity terms on top, right, over the inertial forces. Okay, now why is this important? So Navier-Stokes is sort of famously unsolvable. Like there's a few movies about these famous mathematicians trying to find, solutions to the Navier-Stokes equation. And essentially what we mean when we say we're solving an equation is, in this case, we're trying to find a velocity field. Like you have a problem and you want to know the velocity across each location. And by taking these groupings, we dramatically simplify the terms that are at play in these equations. So for example, let's say we ask the question, are gravity forces important or not? Well, we don't know that, right? So you have to solve out the whole equation. But if we look at this grouping here, so now we know the grouping of the gravity forces. So this dimensionless parameter tells us whether or not gravity forces are important. And we can see from looking at that. So we look at that, okay, now G is a constant, right? We're here on Earth, so 9.81 meters per second squared. So whether or not gravity forces are important is dictated by this gravity force term. If it's large, they're important, and if it's small, they're unimportant. So we see right away, if they're small, right? So if L is small, if our length scale is really small, which is what we're talking about, right? Microfluidics. So if our length scale is very small, gravity forces are unimportant. So when I do my research on microfluidics, I know gravity forces are unimportant at small length scales, right? The other thing, there's one other term though that can make that small. Velocity as well, right? So if the velocity is very high, that term becomes very small. So at extremely high velocities, we also have a situation where the gravity forces are not important. They don't contribute to the solution of this velocity field here, right? And that's incredibly powerful to simplify this equation into forms that are solvable. Same thing with the Reynolds number. The Reynolds number multiplies out these grouping of terms here with these second order differentials. That grouping makes it extremely hard to solve this problem. So again, if that ratio is very small, I can just eliminate those completely from the equation, and it's way easier to solve in that case, right? Okay, now that's great if we have the governing equations. If we already have the differential equations, this is awesome. We can non-dimensionalize them, find our groupings. Wonderful. But when we started this section, what I mentioned was dimensional analysis gives us this power, right? To just take a problem statement and just by looking at the dimensions, we get an understanding of the nature of the solution. Okay, so in lots of cases, we're not going to have the differential equations already, right? And in essence, a lot of what we're doing in dimensional analysis is avoiding the calculus that has to take place. Okay, so what does that mean when it says we look at the dimensional structure? So this is what we're going to be looking at now. Let's take a look at the dimensional structure, okay? And let's talk about what that means and look at how do we take the dimensions of the problem. So let's start with an example here to just see what sorts of conclusions we can draw purely by looking at the dimensional structure of a problem. Okay, let's draw out a little pipe. So we'll look at some pipe flow here. And we're going to say this represents an artery in our body for blood flow, right? So I'll draw in what we know about this. So we're going to say we have our flow rate. Volumetric flow rate is Q here. We have a radius of this artery. And we have a pressure difference as it flows along the artery. Now we know from our undergraduate fluid mechanics that in a pipe, right, this pressure difference across the pipe is proportional to volumetric flow rate over radius to the 4. And that's our dimensional structure. So we get this by recognizing the dimensions. Now let's say you eat a lot of really fatty steaks. You could get, say, approximately a 10% reduction in the radius of your artery. So in that case, we want to find out how much harder does our heart have to work? So let's rearrange this for the two cases. So we'll take if R2 equals 0.9 R1, so 10% reduction. Now we rearrange this so our delta P2 equals Q over 0.9 R1 to the 4, which equals 1.5 times Q over R to the 4. And now we compare the delta P1 before we had the radius of our artery reduced, and we look at the comparison to delta P2 after we have our radius reduced, and we see that the heart has to work roughly 1.5 times what it did before. So that's 50% harder your heart has to work to get that pressure difference to flow the same flow rate of blood through your arteries. Right? Now that we got all that just from looking at the dimensions, right? So that's the kind of thing that's super powerful. Okay, so let's start to break down sort of the basic ideas of what's going on here and put it in a format that that we can use. So it's a tool that we can use a little more readily. So a lot of courses we've done in the past, they've been really interested in a numerical answer. Tends to be what engineering courses focus on. So you substitute a lot of numbers, you get this numerical answer, but underneath that, you a lot of times can miss the sort of underlying structural features of a problem, right? And you can sort of miss that deeper understanding, and that deeper understanding is what can make us really powerful engineers, understanding why the different variables, what do they do to the problem? Why does it change a certain way when we change a certain variable, okay? And let's look at an example here. We're gonna see that by looking at the dimensions alone, we can get most of the answer that we're looking for, right? Without subbing in all the numbers, okay? So we've got here an example. I'll sketch out a little figure here. So a projectile of mass m has an initial height h above the ground. It's projected horizontally in the x direction with a velocity v naught, and we need to find the horizontal displacement when the projectile hits the ground. Okay, so I'll sketch this out. Very simple problem. Now, you might have come across this in high school or maybe first year, and you learn this. So you learn that z is a function of time, and it's equal to -½ gt squared plus h. So when z equals 0, our final time here equals square root of 2h over g. Now we use that final time to get our x value because we need the horizontal displacement. So our x at the final time there equals our velocity, v naught, times the time. So it's equal to v naught times the square root of 2h over g. Usually you just leave it like that. I'm going to rearrange it right now and write it in another way. So we could also rearrange it into this dimensionless form here. So now we've got our dimensionless distance or dimensionless parameter on the right there, and a prefactor constant, we'll call that. So that's root 2 there, just multiplies out the parameter. And in this problem, h is our basic distance here, right? So we're scaling to that in this problem. And we can describe our final displacement relative to this h dimension, because that's a feature of the problem, right? So we can see that the answer here is actually a relationship between two dimensionless groups. So we've got dimensionless horizontal displacement, and we've got our dimensionless parameter. Okay, now let's take a look at another approach. We could have taken another approach here. We could have used the dimensions of the problem instead. And, if you don't have that high school solution memorized, you can actually begin, let's just do a dimensional analysis on this. So what we would do in this problem is you'd normally just take a force balance, right? So our force in the z direction equals mass times acceleration. So we can rewrite here mass times acceleration in differential form, and the body force, gravity, is pulling downwards on it. That's our force balance on our object. So typically you'd take this, you'd integrate it, and you'd solve it, and you'd do all the calculus, but let's not do that. Let's instead just non-dimensionalize this. So we've said h is our scaling factor for the dimension. So let's write that out. And for time, we're just actually going to pick a TC, like a characteristic, we'll call it, or a typical time scale of the equation. And we'll see the structure of that in a second. So I sub all this in, following, the basic format we did in the earlier section. And now we mentioned, so we want to make all these terms roughly order 1 in this equation. So we can do that. So we need to set our characteristic time, right? That makes this multiplier 1. So we choose then, when we simplify this, TC equals the root of h over g, right? So we say then our characteristic time is approximately equal to the square root of h over g. We also have our equation for the x final, our final horizontal displacement. Let's write that out. So that's v naught, of course, times t. It's the velocity that it's moving in the x direction, right? Is v naught. And so now we sub in the characteristic time, right? And we see that x final is approximately equal to square root of v naught squared times h over g. And so we have the basic structure that we had in the previous problem without actually solving through the calculus. We'll write it out like x final over h is proportional to square root of v naught squared over gh. We don't have our prefactor, of course, but we know this proportionality, oftentimes that's enough. That's enough to tell us as a designer, what we need to do. For example, like what happens if the height is doubled, or what happens if we want it to move, twice the distance in the horizontal direction. We have this scaling here. We understand the problem. Okay, now let's walk through some of the basics of dimensions and units here. This is the core kind of what we're covering here. So in mechanics, we commonly use mass, length, and time. So for example, for Newton's second law, force equals mass times acceleration. So mass is our m, acceleration is our length over our time squared. So the dimensions of this are ml over t squared. And the units of force, SI units, are newtons. Okay, so let's fill out this table here. some common variables and dimensions in mechanics. And as we go through, these dimensional analyses, it really helps to know that like a Newton is a kilogram meters per second squared. So I'll write the dimensions out, with their SI units and their fundamental units as well. Like knowing that a joule is a Newton meter, like that can be really helpful as well. Power is joules per second. And then, if we did need temperature, we would use degrees Kelvin. Okay, so moving forward here, we're going to look at a systematic way to approach this, right? Because you've probably seen the examples I've done so far and said, okay, like wonderful, Professor McDonald already knows the answer, and so he can go back with this dimensional analysis and tell us what we already knew. But if we have a systematic approach, we can all apply this to the problems that we see, the problems that we might need to solve in our research, right? So what Buckingham-Pi theorem says is it's basically saying given n variables that are expressible in terms of r dimensions, there's a total of n minus r independent dimensionless parameters. In mechanics, we mentioned we have m, l, and t, so r equals 3. If we did have temperature, which is common, really common as well, we would have m, l, t, and phi, so r equals 4 in that case. Okay, let's do an example. It's always good to see how this works, and I'll choose a pendulum, right? So again, it's something we do understand the solution to very well, but this just really emphasizes the power of our dimensional analysis. Okay, so I sketched that out first, this pendulum here. We're given the governing equations there, and what that helps us do is it helps us see the important variables. And so what is it saying here? So pendulum is initially at theta naught, as seen in the figure there from the vertical. Neglecting air friction, find the period of oscillation, tau. Okay, so we have 5 variables, right? Tau, mgl, theta naught, it's 5. Buckingham-Pi tells us n minus r. So we have 5 minus 3. 3 is our mlt. And so we're going to have 2 dimensionless parameters that govern this equation. All right, so let's do a Buckingham-Pi analysis. You might have seen this in undergrad. It helps to do this again here so we can all remember what's going on. And I'm going to do it systematically. Okay, so first let's write these out with their dimensions. Tau, mg, l, and theta naught. So I'll write the corresponding dimensions below them. We're going to select repeating parameters. And trick for this is generally you pick the most basic 3, or essentially you want to pick the ones that you're not interested in analyzing. So we know we need to find the period of our oscillation. Tau, so we're not going to pick that one. So M, L, and G, and of course those are 3 basic parameters that are fundamental to this problem. So to do the first grouping here, we write pi 1, and then we take our repeating parameters and we give each of those a general exponent. So m to the a, l to the b, g to the c times tau. Okay, and then we sub in our dimensions for those. So that's the capital M, L, and T for time. And we say that's equal to, we want it to be dimensionless, so it's equal to m to the 0, L to the 0, and T to the 0. That's how we make it dimensionless. So now we just have algebraic equations. So I'll write those out here. We solve those and we get the exponents there. So then when we write that out, so our pi 1, these pi's, right, these capital pi's, that's our dimensionless parameters. So pi 1 is the tau times the square root of g over L. And our pi 2 is theta naught, right? Theta naught, the one that we had initially there that was already dimensionless. Okay, so we know, therefore, 2 dimensionless groupings. So we have tau times the square root of g over L equals a function of this theta naught, so this starting angle. Okay, so what does this result tell us? First, so if you did an experiment, right, where you plotted theta naught versus this tau times square root of g over L, right? So you could vary, for example, L and theta naught, and you would have a plot here, and you could actually figure out what this function of theta naught is. Okay, now we keep in mind that we were asked for the period of oscillation. Okay, so I'm gonna rewrite this grouping here to isolate tau. So we can write tau over the square root of L over g is a function of theta naught. I'm just rearranging that. And now if I do an experiment where I fix a value of theta naught, right? So for each value of theta naught, that on the left is going to be a constant. So we know that tau must be proportional to our L over G, square root of L over G. So we can write that as L over G to the half. And so if I plotted this, right, on a log scale, I'm going to end up with this line. And the slope is like this. And these are different values of L, for example. So if I vary L, right, while I'm measuring the period of oscillation, I end up with a line like this. And you can see I can actually tell that. So I could have actually just looked at the dimensions of the problem also and said, well, tau has a t in it, so I know that has to be proportional to the g and the L terms there, and this grouping that we have here is the only way to make the dimensions balance. So you see, it's all just dimensions, right? And again, I know, you see, I don't need numbers all the time, right? Like if I want to vary the period of oscillation, I know exactly how to do it. right? I know exactly what I need to do with L to make this work for me. Okay, super powerful, right? Let's do another example. This example is like shockingly powerful. So there's this story, so it's actually famous and true story. It's actually told by G.K. Batchelor in a publication in 96 called The Life and Legacy of G.I. Taylor. So the story is that the Americans were testing the atomic bomb in 1947, and the energy of the bomb was highly classified, right? But there was these photographs of the blast of this nuclear explosion published in Life magazine. And so he just used dimensional analysis with these photographs, and he actually figured out the energy of the atomic bomb. And apparently, as the story goes, he was actually admonished for publishing his results, even though they were based on publicly available information, right? So this is the essence of an example to show just how powerful a dimensional analysis can be. It's crazy. Actually, so interesting story. There was the Beirut explosion recently, and so some people took this exact same approach with pictures of the Beirut blast, and you could estimate exactly the energy in the explosion that was in that port building there in Beirut. Okay, so still super relevant, very extremely powerful analysis. So we start our analysis with two assumptions. So we say the bomb energy was released in a small space and the shock wave was spherical. So we have the pictures, right? I've even shown them there at the left. Those are the actual pictures. So we know that the radius, like the size of the explosion, right, is a function of time. We can clearly see that changing with time. But we also know that that radius is going to be a function of the energy, the bomb energy, time, of course, and the density of the air. The density of the air that it's traveling through is going to change the size of that sphere. Okay, so those are our variables there. We have 4 of them, R, E, T, and rho. 3 dimensions, M, L, and T. So 4 minus 3 is 1. We're going to end up with 1 dimensionless parameter. So we read out the dimensions corresponding to each of the variables. Pick our repeating variables. So R is what we are interested in. So we pick E, T, and rho for this one. There's only one dimensionless parameter, so it actually doesn't matter how you do it in this case. So our pi 1, our single dimensionless grouping, we take the dimensions, give them an exponent, and then equate that to our dimensionless m to the 0, L to the 0, T to the 0. Now we have our algebraic equations. We solve out those. So here's our final parameter. We only have the 1. Okay, so in that case, we say it's equal to a constant then. So we write that then, therefore, so the energy equals some constant times density times r to the 5 over t squared. Now we have our image, so we can plug this in. So at t equals 0.006 seconds, our radius is about, we'll say, 80 meters. Density of the air is 1.2 kilograms per meter cubed. Okay, so we can go ahead and sub all that in. So we end up with some constant. So the constant, we can go ahead and assume that's equal to 1. And that gives us an approximate energy. So that's 10 to the 14 kilogram meter squared per second squared. That's roughly 25 kilotons of TNT. Okay, very close estimate to the actual energy of the bomb. So fascinating. Again, if we do want the numbers, again, you can see how to do that here with a dimensional analysis. Super, super, super powerful. And you can see this really transcends microfluidics. So of course we use a lot of this, right? Microfluidics involves small scale flows. Extremely helpful, very powerful, but this is a tool that really transcends a whole bunch of different fields. You can use this dimensional analysis in a lot of different places. Very, very powerful. And just quick summary. So what we did was a dimensional analysis today. We looked at essentially when you have a problem. If you look at the dimensional structure of that problem, you can figure out many things you need to know about the answer. Okay, and so we did a bunch of examples. So we looked at how to non-dimensionalize when you have a differential equation and how powerful the different dimensionless parameters can be in telling you which terms you need to keep or you don't need to keep, thus simplifying your math tremendously. And we also just looked at, even if you don't have the governing equation, you can do, Buckingham-Pi analysis to figure out how many dimensionless parameters govern the problem. And then again, you know a lot about the final form of the solution just from analyzing the dimensions. So that's all for this video. Thanks for watching.